Check, check, check. Hey, can you hear me? People join online. Good, thank you. Okay, good morning. Let's get started. The last couple lectures. So hopefully today I could finish all the lecture contents. Okay. And then we'll use the last lecture to do a quick review. And just a review of what we have learned in the previous lecture. Okay. So we used probably 1.5 lecture already on the Fourier series. First, we tackled Fourier series using a so-called trigonometric form. So first of all, Fourier series deal with periodic function. And these two formula here, those are directed from the formula sheets. Okay. So these two constitute the trigonometric form for a Fourier series. The fundamental skill that you will have to make is just basically integrals. Right? You do 3 integrations to find the values for each one of the constants or coefficients. The reason it's called the trigonometric form is pretty straightforward because it's all in the trig function format, right? And then from here, there's a different way to write it. Okay, different way, but it doesn't mean it's a different, describe it differently. Okay? So still the same periodic function. And I probably should change these to f. So this function f can be written in a so-called compact form. If you compare this compact form with the trigonometric form, okay, obviously, these two terms combine into one single term as a cosine, and then there's a phi angle showed up at here. Sin is what we call the amplitude. So this is called the compact form. Okay. And last format is what we're going to do today, is to look at another format called the complex format of the Fourier series. So let's take a look at this together. How can we write, basically, this is your original one here. How can we write this original trigonometric form into a so-called complex form of a Fourier series? Okay. And sometimes it's also called exponential Fourier series. So here's what you do. It's mainly to use the Euler's formula. Okay. So recall the Euler's formula. And that is e to the power of, let's say you put a t here, e to the power of jt, and that's exponential, basically exponential format. And that equal to cosine t plus j sine t. Okay. Now, if in our case, we actually will show is j omega naught t. Okay. So just put omega naught in front of t is the same thing. So you get a cosine omega naught t plus j sine omega naught t. Same thing, just t change to omega naught. This is the Euler's format. And from this Euler's formula, if you recall that we have an immediate identity. So for example, let's see, if I write this cosine t, and I can write it in terms of the Euler's formula. So cosine t basically equal to e jt plus e negative jt divided by 2. And you could easily verify if e to the power jt equal to this, then e to the power negative jt equal to cosine t minus j sine t. So you add these two terms together and divide it by 2, and you get cosine t, right? And similarly, you can get sine t, right, equal to e to the power jt minus e to the power jt divided by 2j. Good? Yeah. Same thing. If you use this term minus this term and divide it by 2j, and you get sine t. All right, so this is a Euler's formula. Okay, so how we can use this information to rewrite this trigonometric formats of the Fourier series into a so-called complex form, as we've shown over here. All right, so now let's go back to the periodic function. Consider this periodic function, and we have shown that, and I'm just rewriting the Fourier series formula, that equal to this an cosine n omega naught t plus bn sine n omega naught t. So this is what we have obtained. Okay, good. So now you look at this current formula. It has a cosine and sine, okay, in this formula, which this is why we call it trigonometric. So I'm going to replace this cosine n omega naught t and the sine n omega naught t with the formula that I have just written down at here. So cosine t equal to this, sine t equal to this. Now here I have cosine n omega naught t, right? I mean, so technically it's not much a difference. You could just write the same thing. Cosine n omega naught t, you change the t to n omega naught, that will equal to e to the power j n omega naught t. Negative j n omega naught t divided by 2. So that's what I mean. For cosine omega naught are using the formula. Same thing, you can write down what sine n omega naught t using exactly the same formula over here. And replace these two, okay, with the exponential or complex numbers. Okay. So if I do that, then what does this f of t become? So f of t, draw an arrow here, so you replace, or in other words, you're replacing this with this. So f of t equal to a naught summation sign goes from 1 to infinite, and then an. So cosine n omega naught t equal to e j n omega naught t plus e negative j n omega naught t divided by 2. Euler's formula. Sine n omega naught t is e j n omega naught t minus e to the power negative j omega naught t by 2j. Okay, so and now you don't have sine cosine specifically showing in the bracket anymore. What's showing instead are those exponential complex function. Right? Okay, so the next step, we will sort things out a little bit. So how we're going to sort things out is, so basically you can clearly see you have a term associated, if you expand every term, you have a term associated with this e to the power j omega naught t. you're also going to have a terms associated with this e to the power negative j omega naught t, right? So this 2j, you can easily convert it into, you can easily get rid of the complex number in the denominator. So you could just multiply 2j at the bottom and then 2j at the top, or negative 2j, okay? So then you will get rid of the complex number on the denominator. So then you group all the similar terms. All the similar terms in all the terms associated with this one, and all the similar terms associated with this one. And if you do that, so we're going to get an minus jbn divided by 2 e to the power jn omega naught t, and plus an plus jbn divided by 2 e to the power negative jn omega naught t. So nothing changed, just you grouped all the terms associated with this e to the power positive j omega in omega naught t with the term e to the power of negative j omega naught t. Do try it. Okay, you can try it, see if you can get this expression. Okay, so now from here, and we're not going to do more of simplification anymore. Okay, we're going to define some constant for ourselves. First of all, we're going to let d naught equal to a naught. So this a naught, I'm going to let a naught to be the same as a new symbol called d naught, and then dn equal to an minus jbn over 2. And the d negative n equal to an plus jbn over 2. So the symbol, if defined it just like this, just to get used to the last two here. Okay, so what the last two basically means, if you plug n equal to 1, d1 equal to a1 minus jb1 over 2, right? Now, if you plug n is 1, so then it's negative 1, so this becomes a negative 1 plus jb negative 1, okay, like that. Good. All right. So based on this definition, this new defined symbol right here, then this f of t that we have just derived, this f of t, okay, can be rewritten, okay, for this expression. First, a naught becomes d naught. Okay. Actually, yeah, you don't write a d naught at here. Okay. So basically, what we're gonna do is, right? So this n initially it goes from 1 to infinite. So with this notation here, dn d negative n, then this f of n, okay, see if you can accept that. The n here, I can let it go from negative infinite to positive infinite. And the expression for I'm make sure I have it right here. Yeah. An expression for the summation sign here is dn e to the power negative and e to the power of jn omega naught t. Okay. So let me write down this and see if this notation actually is just a different way of writing of this expression. Okay, so let's take a second examination at it here. Right. So first of all, I can use some substitutions to verify. For example, right? So this goes from negative infinite to positive infinite. Now, if n equal to 0, if n equal to 0, then this whole term here, you get just d0, right? So which is a naught. So that's exactly what happens previous, right, over here. So that n equal to 0 worked, okay, when equal to 0 over here. Okay. Now you might argue is you don't have n equal to negative number in the previous expression, right? However, if you look at the previous expression, what do you really have? You have a e to the power negative j n omega naught t. So even though the previous term doesn't have a negative n, but you do have a negative n showing up at here, right? So that's why over the next expression over here, so we simplify the two expressions. We let n start from negative infinite, and the exponential term, right, can be simplified just to into 1, because when a is negative, the negative n naturally showed up over here. Does that make sense? You know, so when n is negative, okay, so you need a negative here. So then your dn, right? This is dn. This is a negative number, okay. And the e also negative n omega naught t, right? But n is negative. So that's exactly what's going on over here. Okay. So this d negative, we can just say this is basically, you got a d, for example, d negative 100 e to the power negative j 100 omega naught t. Right, that's n negative. And that works very well actually with the second term. That's basically the second term over here. So this d negative 100 basically is this a 100, yes. So a 100 plus j b 100 over 2. Right. And that e term here is still this e to the power negative j 100 omega naught t. So this notation, okay, it's very much as far as you can compact the two terms together into this one single complex exponential format. So this expression here, this is actually what we're looking for. It's called that complex form of Fourier series. Okay, so this is basically called the complex form of Fourier series. Okay. A couple of observations. Okay. If you compare this dn with d negative n, so you have this dn expression for an minus jbn over 2. You have a d negative n for an plus jbn over 2. So these two, okay, clearly these two are what? See, just a sign difference. One is negative, one is positive. So according to our definition, these two are called conjugate. Okay, they're conjugate complex. Okay, conjugate to each other. Okay. Now, second thing is, okay, so the dn, basically, as long as you get the dn, and you can get d negative n, right? So essentially, your dn conjugate, when you put a star here, means this is conjugate action, right? So 3 plus 2j is conjugate equal to 3 minus 2j. And that's what it means. And dn, right, as you can see, is an minus jbn over 2. And we can show that, so without the proof giving it here, and we can show that this is equivalent to 1 over t naught, 0 to t naught integral f of t e to the power negative jn omega naught t dt. So dn, we can show that this is equal to this. So essentially, you can calculate the dn, okay, either by calculating a and b in first, and then calculate dn, or you can just directly using this integral to calculate this dn. So I'll show you an example next. Okay. As a matter of fact, if I just focus on this portion right here, okay, and this is actually next we're going to learn. This is essentially a Fourier transform formula. It's not quite exactly the same. The limits will be a little bit different, but what's over here essentially is the format of a Fourier transform. Okay. I think so we'll come to that. Okay. So overall, as if I go back to the beginning of the formula sheets, right? If there's a complex form, then this is the formula. This is how you calculate d naught, and this is how you calculate dn. And that's about it. Good. So let me show you an example of how we can write a complex, well, we can write a Fourier's periodic function into a complex formats. Now, before I proceed to, maybe let me finish the example, then let's talk a little bit about. So let's say I have a periodic function. It's basically box. The box from negative d over 2 to positive d over 2. All right. So this is how the box is distributed, okay, on the time in the time domain. Negative. Amplitude is, let's see, A. So first, when you're presented with this graph, it's always the first fundamental skill is what is the period of this function. So first, you need to write down the period of this function here. And as I suggested, I mean, you can literally start anywhere, and then you go to the right side until it starts to repeat itself. Then, right, the distance you traveled along this t-axis is the period. And in this case, it's pretty obvious. Basically, if you start here, right, and if you start anywhere here or here, doesn't matter, right? You go up to here and then start to repeat itself. So the period here is just capital T, right? Capital T as shown in this graph here. So once we know the capital T, okay, or the period, so then I can start to apply formulas. Okay, as I said, we need to write it into the complex. Okay, so we'll write the Fourier series in complex form. So the formula we're using essentially this dn and also the d naught, right? So d naught, first let's calculate d naught, right, equal to the original formula t naught. So you use exactly the same formula for calculating t naught. And that's the formula for calculating a naught, or in this case, we're going to call it d naught. So integrate within one period, 0 to t naught, integrate this f of t, and you look at the integral at here. So technically, 0 to t naught means from here to here, right? From here to here. And you can do this 0 to t naught, or alternatively, right? So now I didn't show this in the class, but when you integrate a periodic function, right? So As long as you're integrating within one period, the value will actually be the same. Okay, so I could integrate from negative t over 2 to positive t over 2, okay, instead of from 0 to t. Okay, so you could do any one of this, okay, as long as you're integrating over one period. Okay, the value of this results, okay, should be the same. So technically, I could just integrate, because if I go from negative t over 2 to positive t over 2, f of t exists only between negative d over 2 to d over 2. So you can just simply just d over 2 to d over 2. Then f of t's value is a dt. So that's how you get this integral. And you get a times d over capital T, if t not equal to capital T. Same thing. If you integrate from 0 to t, then your integral from 0 to d over 2, and then you calculate from here to capital T, right? It's the same thing. You get the same result. So you get the d naught. And now let's calculate this a at dn. Formula dn is 1 over t naught, okay, and 0 to t naught. Okay. Actually, if you look at the formulas I showed you over here, right? If you look at the formula, general formula show you here. The general formula didn't specifically say it has to be 0 to t naught. It actually says you can start anywhere. You can start from a location 3 or 2 or 4, doesn't matter, the 8, right? As long as your integral period, right, limits give you one whole period of t naught, right? The upper limit minus the lower limit, you get a t naught, and you get exactly the same results, essentially, okay? So anyway, I'll just put this 0 to t here, and then f of t e to the power negative j n omega naught t dt. That's your dn. So let's calculate the dn here. Again, I can do exactly the same thing as I calculate this d naught. Instead of going from 0 to t naught, so we can go right from negative 2t to t over 2, f of t e to the power negative j n omega naught t dt. And again, there's only the f of t exists only from negative d over 2 to d over 2. And the value is a e to the power negative j n omega naught t dt. Okay, from here, it seems to be confusing integral, but keep in mind, you're integrating dummy variable with respect to t, then everything else, just treat them as constants, right? So you have a j, you have an n, you have omega naught. So you all treat them as if they're constants here. Okay. You just integral with respect to t. I think everybody knows how to integrate an exponential function, right? Or negative t or dt or whatever, right? Or you have a negative at, right? So that exponential function, integral of this exponential function here is no difference from integral of this exponential function. So the results, okay, for t naught, right, is basically capital T in this question, a over capital T. The coefficient in front of t here is negative j n omega naught. So you get 1 over negative j n omega naught integral, right, of e. You get this, and then e to the power negative j n omega naught t, and t go from negative d over 2 to positive d over 2. If you take derivative of this one, you should get back exactly what you have for the integrand. So plug in the limits here, and you get AD over capital T. And fortunately for this question, the J term actually disappears. So this is the results of this integral. It's a real, okay? It's a real number. But usually, okay, in most cases, this should be a complex number for dn. But just in this question, it gave us a real number at here. Okay, so that's the end of the results here. So you get the d naught, you get dn, so then you get basically the writing of this complex form of Fourier series. Now, usually what in the future when you learn more of a Fourier series, okay, so we can go from here to plot. Okay, we can go from here to plot the magnitude of dn and also the phase angle of this dn, okay, to give us a so-called a spectrum plot. So amplitude spectrum and phase spectrum. So the magnitude is shown here. So you can see magnitude plot here is absolute value of the magnitude, okay? So the sign, of course, oscillate from negative, positive, but once you put the absolute sign, you can see the magnitude here is all positive number now. Now, phase angle certainly has a negative and a positive showing up here is because when it's negative, it's negative pi. When it's positive, it's pi. Okay, that's the oscillation. So that essentially tells you the distribution of the frequency within this signal, okay, and also its associated height or amplitude. So there's quite a bit of a frequency centered around a 0, omega equal to 0, but then it started to decrease, right, as omega goes to a higher frequency. So that's sort of tell you some information behind that box over there. So as I mentioned, this is not going to be tested in the final exam, but I think as a complete package of Fourier series, there are 3 ways to write Fourier series: trigonometric, compact, and complex form. So in the final exam, I think the focus you should be on this trigonometric form. So if you test, that will be part of the test. I think there should be a question on that. Okay. Any questions on Fourier series? If you're going to mechanical and electrical, and I think in civil you should also probably, because in civil there are quite a bit of a course content on signal processing too. Sometimes you do vibrations of a building, right? You also do maybe processing of data coming from maybe a sensor mounted on the bridge, So inevitably, this Fourier series or Fourier transform will be a tool for you to use it to process signal. Okay. All right. So last topic, okay, is Fourier transform. So I'm going to just quickly touch upon this. Okay. And I'm almost 100% sure that people are losing interest to look at all these different formulas. Anyway, so let me write it down. I think we actually will be able to see some connections between Fourier transform and Laplace transform. Okay, so first of all, the Fourier transform definition. Okay. So first we'll consider a general function f of t. So when we say general function means, remember what Fourier series, right? Fourier series deal with is a periodic function. So now I'm not necessarily restricted to the periodic function for a Fourier series. And we're just dealing with a general function f of t. Then I can conduct the following transformation on f of t. So here's the formula. You integrate f of t multiplied by e to the power j omega t and integrate with respect to t from negative infinite to positive infinite. And you will get a function of omega because, right, you're integrated with respect to t. Once you finish with this integral and you're left with just a variable omega. And of course, you also have the complex information in it. So you're going to be left with just a function of omega here. So omega here, we call it, we typically call it, it's a frequency. Okay? So omega is a variable, okay, for this f of capital F of omega. And you plug in different frequency value, and you get a different capital F value. Okay. So essentially, this formula transforms f of t to capital F of omega. And it's just like a t domain, right? This is f of t is in t domain, and this is in the frequency omega domain. And remember Laplace? Laplace is what you transform f of t to a s function, or capital F of s, or from t domain to s domain. And actually, there's a connection. I'm going to point it out later. Okay? If you recall this, s, I mentioned the s equal to sigma plus j omega. S is also a complex number. Okay? And the only difference is s has real parts, sigma, but over here, right, this is just a omega here. So sometimes people also put a j over here, okay, because there's a complex. Okay. So essentially, actually, kids, let me maybe put it down here. There's a very quick connection, but it's not very rigorous. Okay. So if you look at Laplace, if you have a Laplace transform capital F of s, and if you let s equal to j omega, so from here to here, right, and you get Fourier transform. Okay. This is not always true, but in a lot of time it's true. It's not a very rigorous statement. However, in many functions, and you'll find that this actually is true. Okay. So what's so useful by the Fourier series, right? First of all, so this FFS is a complex number. And it's complex number, then you can, for any complex number, you can always write it as an amplitude and as a phase. So if you have a complex number over here, then you have an amplitude R, you have a theta here. So you can always write it, right, as R times EJ theta for a generic complex number. So in this case, what we will see is the amplitude is a function of omega. So it's amplitude function omega, and the phi, okay, so technically is also a function of omega, okay, or frequency. So this is the phase. So after transformation, using Fourier transformation, the previous time domain function change into a complex function as a function of omega. And then you can easily extract the amplitude information and the phase information out of this f of omega, which you do not see that actually in the time domain directly. You can only see that after you transform it. That's why we call sometimes changing perspective, right? So you cannot see through these things from this angle. You had to see through things from a different angle. That's called perspective. And there's a very funny picture. As a matter of fact, I want to mention here, we mentioned so many famous names, Lagrange, Euler, Fourier, right? All of these are French mathematicians, physicists, brilliant people. So you actually, if you ever go to Eiffel Tower, I haven't been there. If you look on this column here, okay, or the row there, you actually will see all the names of these French brilliant scientists or mathematicians' names engraved on this Eiffel Tower. There are 72 names. Of course, Lagrange is right here, okay? Laplace right here, Fourier probably somewhere on the other side of the tower. Okay. And I doubt people actually notice that when they visit the Eiffel Tower. Now this one, people getting a little funky engraving, tattooing the Fourier transform on their arm. Unfortunately, it's wrong. So it should be, if you look at this here, it should be IG omega x, okay, instead of a 2 pi. So anyway, so my point is, not to elongate with too much of. I just want to give you a bigger pictures. Okay. So what is the connection? We talked about Laplace transform. We talked about Fourier transform, and we also talked about Fourier series, right? So you need to basically in your head as a bigger picture. Fourier series, you're not changing it to a different domain. It's still time domain. Okay, first of all. Okay. Laplace and Fourier transform, you actually changed to a different domain from t to something else, so a to s or omega. Now for Fourier transform, so both these transform actually are used in a different applications. So Fourier transform is very widely used in signal processing or signal or image processing or analysis. So that's what your Fourier series is all about. And Laplace transform, are very much used in control applications. So control system is where something you learn in your third year. There's also professions basically called controls engineer. So when you do control applications, right, you have a system, you want to control the behavior of the system. You want to say you give an input to the system, you want the output to follow the input, for example, right? That's called control system. So you have to design something and put it in the loop so the system actually behave the way that you want. So when you do that, part of that controller design very much depends on, especially for linear system design, very much depends on Laplace transform. Okay. Actually, the Laplace transfer function that we covered is exactly part of this controls engineer application. Okay, so that's a little bit difference between this Fourier and Laplace transform. And some of the connections, as I pointed out, if you have a Laplace transform, okay, in most of the time, you could just simply let s equal to j omega, and then you get the Fourier transform. Not all the time, okay, not all the time. Okay. Unfortunately, I don't have a lot of time. I don't want to give you too much of examples, but just like when we learn Laplace transform, okay, we can also write down, Fourier transform of some typical functions or signals. So you can also write down very similarly to Laplace transform. So let me just maybe write down one of them, okay, just to give you an illustration. And so let's say I have a function f of t equals to delta t minus t naught. Okay, so delta t minus t naught refer to a impulse function it shifted from t equal to 0 to t naught. Okay, that's your delta function. Okay, so then what is the Fourier transform of this impulse function? So we, instead of a big L, we put a curly F in front of this bracket, representing a Fourier transform operation. Okay, so substitute it into the formula. This is directly substitution application of the formula Fourier transform. So delta is right here, right? And this is where you will make use of properties of an impulse function. So when you multiply any time function with a delta function, or shifted or non-shifted, doesn't matter. And because delta function exists only at the t naught, then this exponential term, which originally is a function of t, so you can replace the t with t naught. So now this is not a function of t anymore, so you can take this out of the integral. Right. Take it out of the integral. And now finally, you're just integrating from negative infinite to positive infinite of this impulse function. And can anybody tell me what's the result of this integral function? Exactly, excellent. Right, area underneath the impulse function is 1. So you're just left with, sorry, e.g. omega t naught, right? So that's your Fourier transform of the of this impulse function here. Right? If t naught equal to 0, right, if t naught equal to 0, then this f of omega just become the Laplace transform of delta t. So you plug t naught equal to 0 into this function, and you get 1. So Fourier transform of impulse function delta t is 1. If you look at the table for Laplace transform of delta t, which is also what? Also 1, right? It's also 1. Okay. So this actually reveals quite a bit of information in here. Okay. The information is, if you look at this one here, right? So basically, the Fourier transform of impulse function is a constant 1. Then if I'm going to plot the magnitude of this f of omega versus omega, this is f omega versus omega for the delta t, what am I going to get? I'm going to get a constant amplitude 1, right, the plot. And this plot tells us a very important information, because you see, doesn't matter what the omega value is, you have a presence of amplitude of 1 everywhere. So in other words, this delta t, right? This delta t, let's say the delta t is right here, or even that one, doesn't matter, right? In the time domain, all you see is a impulse with infinite amplitude at t equals 0. Now that's what you see in the time. But once you transform into the Fourier series, the Fourier transform, and now you can see that impulse contains an infinite number of component frequency, and they're all equally weighted with 1. So behind the delta function, there's so much frequency, infinite, literally, right? Literally infinite frequencies exist. So this is why delta function is so much of a wanted function by a controls engineer. People wanted what? They want to be able to create a delta function so that they can give this delta function as an input to a system. Why is that? Because delta function, as you can clearly see, contains all the frequency components. So if you can actually put this delta t into the system as an input, it's equivalent to say you're injecting the system with an infinite number of kind of frequencies information. So that's why the impulse response, which is corresponding, the output corresponding to impulse input, is so precious, because that impulse response tells you the system behavior corresponding to all different kind of frequency inputs. Right? That's why this delta t is a very much wanted function, but however, you cannot create it experimentally. Okay? You are able to obtain it analytically, right? Okay, so that's why this delta t is so good. Okay. Anyway, I'm gonna stop here. Okay, There are other examples of Fourier transform. You can take a look at the lecture notes. Okay. Don't think I'm going to spend too much on that anymore. I will just go through some lecture content next lecture. Okay.